All right. Okay. Thank you all for coming. It is a great pleasure to welcome Professor Paul Chaikin back to Brown. And Paul just said that I only invited him every 20 years just to make sure he's still alive. And I'm very happy to say that, Paul, you're still alive and well. And then very strong. Okay, so Professor Chaikin got his PhD from UPenn in the 70s, and he went to UCLA as assistant professor for a short time, and then he went back to UPenn for a long time as a professor, and then he went to Princeton, and then for many years, and then finally he went to NYU. And then the way NYU got him to leave Princeton was offer him this 360 degrees view of Manhattan. So you can't reject that, right? So, and it's free.
It's not free.
Well, okay. So for the students here, let's see how which title of Professor Chaikin that will impress you. Okay. He's a member of National Academy of Science. American Academy of Arts and Sciences, and then I guess you are not impressed by that, and then he's a author of this book. Now impressed, right? Okay.
Co-author.
Okay. So if you want him to sign it, I had my copy signed some 20 years ago. So I had 4 copies for my students of the same book in the lab. Okay, so Professor Chaikin made many contributions in spin density waves, in counter effect, in superconductivity, in charge density wave, and then over the last 20 plus years, he made a major contribution to nanofabrication, self-assembly, the famous hard sphere problem, for which he received the Buckley Prize. Now you're impressed. Okay, now let's welcome Professor Chaikin.
Thanks, Sean. I'm really looking forward to the next time I get invited 20 years from now. If I make it that long. Okay, so only 2/3 of what we told you is true. What I'm going to talk about today is a really trivial dynamical model that I came up with to explain a transition from reversible to irreversible flow in low Reynolds number fluids. And it's really a really trivial model. You throw down particles in 2 or 3 dimensions, and if they overlap, you say they're active, and if they're active, you give each one a random displacement from its position, not toward the guy it overlaps, not away from the guy that it overlaps. And this thing just evolves with time, and it gives you some sort of order, but one of the things it will do is it will eventually, as you see here, stop. And this is an absorbing state transition. It now has gone to a state which is absorbing because there's no activity, because they don't overlap anymore. And as you might expect, I can't do this for any filling. If I keep on increasing the number of particles there, eventually I get to a state which can't organize itself so it has no overlaps. And that keeps on evolving essentially forever, okay? And so you have a transition which is not as we'll see, which is not a thermodynamic transition, but it's a dynamic transition. And I'm going to tell you how that led us to some insights in what is probably the oldest and most fundamental question that has existed in physics and mathematics. a problem which is many millennia old, which is the packing of hard spheres. Okay? And that's what's shown over here. Oops. That's what's shown over here. This is Bernal's diagram, Bernal's picture of hard spheres packed on top of one another in the densest form they have. Now, we're going to get some insights from this problem on the packing problem. But first, I should let you know, as you might imagine, that the solution to this problem was known 5,000 years ago, as soon as there was agriculture in Mesopotamia. You know, people, merchants who had fruit stands, learned to pack the fruit in this characteristic way, which is in fact the densest packing. Now, that wasn't so easy for mathematicians and physicists to prove, okay? As a matter of fact, it was originally treated by physicists in terms of the Kepler conjecture. Kepler thought that this would be the densest packing, and he sold that to the British Navy as a way to stack cannonballs on naval ships. Gauss said, well, okay, I can't do this problem exactly, but I can do part of it, and he found that if you choose a lattice, if you chose a periodic placement of the spheres, the densest that you get is FCC, which is here. And the actual proof that this packing, FCC, which looks like this, which the grocers all knew immediately, was done within the past 20, 30 years by Tom Hales in a paper that took 14 years to review, okay? Because there were parts of it that had to be checked. There were a couple, standouts in disordered systems that he couldn't prove, and you just had to look at that particular, do a computer simulation with those particular crystals and find out, or disordered arrays and find out what they give you. Okay, it turns out we're not going to be interested in this so much. What's actually more interesting nowadays is what happens if you look over here. So if you don't take them one by one and place them like fruits in a fruit stand, okay, you just take a box and you pour hard spheres into it, all the same size, all spheres, frictionless if you want, or as close to you get it. You don't get this structure. You get the structure which is shown on the side. This structure, FCC, is 74%, it fills space to 74%. The disordered structure over here, which is known as random close packing, fills space to 64%. And it's lucky that this is true, okay, because there are lots of consequences of them being different. This problem goes way, way back. I'm going to show you in a bit what it says about liquids, solids, and gases, and freezing. But the packing problem, was useful for grocers. The random packing was important because in Mesopotamia, they sold grain by volume rather than by weight. And so if you could figure out a way to pack less densely, okay, you won. You got a lot more money. You could buy your neighbor's farm. You could do all sorts of things. You'd become rich if you figured out a way to pack it poorly. So this is what Bernal quotes from the Bible. In closing, we must not forget the commentary on random packing, which St. Luke attributes to Jesus. It shall be given unto you, good measure, pressed down and shaken together, running over shall men give unto your bosom. For with the same measure that ye mote, withal shall be measured to you again. In other words, don't cheat. Shake it, level it off, make sure it's as dense as you can get it in this random close packing phase. Okay. Now, why is it also interesting to physics? Okay. So when van der Waals first started looking beyond an ideal gas, the van der Waals equation of state, the first thing he put in was not attractions, but repulsions. He said the first thing you have to remember is that your atoms or your molecules or whatever take up space. So the entropy, instead of being the log of the volume, should be the log of the free volume. You should subtract off the volume taken up by the particles, which is just the number of particles times the volume per particle. And you can rewrite that in terms of the packing fraction over here. So it becomes the volume times 1 minus phi over phi c. If you derivate this with respect to volume, you get the pressure, and the pressure, you see, blows up at the critical density over here. So what that means is if I have a ordered state at 74% and a disordered state at 64%, as I increase the density, eventually the entropy is higher. This is higher if phi c is larger, okay? The free volume is larger, and so you can either say you have a higher entropy, or you can say that the pressure is higher in the lower density phase, and you actually push the particles out into the denser phase over there. And what you learn from this is if you have a packing problem like this, the stable densest phase, okay, wins. And that's the structure you go to. And that's why most things freeze, actually. Why most things crystallize. So you're used to thinking of attractive interactions, but attractive interactions are really responsible for going from a gas phase to a liquid phase, increasing the density. What gives you the structure is the repulsion, and this is sort of the easiest example of a repulsive interaction, just the fact that the particles can't interpenetrate. And so this is the proof that just from repulsive interactions, you can get a crystal. Okay. And this problem has been looked at lots of different ways. One of the ways we can look at it is looking at one of Einstein's 1905 papers, where he tells you if you look at colloidal particles, okay, you still get the same relationship. It's an osmotic pressure now, but you get the same relationship between the pressure and the density over here. Okay. He also said that if you have a force, the force acts to change the pressure, and that means that the pressure over here, it turns out, I can get by getting the weight of all the particles on top of it, of all the atmospheric particles, up to the edge of the atmosphere, and that gives us the pressure here. And so you can do an experiment, for example, with colloidal particles, where what you do is you just let them sit, okay, and sediment, and you'll end up with a region over here which is a gas, a region which is liquid, a sharp boundary over here which has these crystallites in it. They're colored because they're Bragg scattering, because the size of a colloidal particle is typically a micron, which is comparable to the wavelength of light. So you're Bragg scattering visible light with this. And here's the phase diagram that you come up with. This is an old paper of ours, where you've got the pressure over here, okay? And here's where you got the volume fraction, and you can see the pressure. This one is cut off because you transition from the fluid phase, from the liquid phase to the crystalline phase, and this goes up and extrapolates to 74%. So that's the crystal phase. So it's important that the crystal is denser than the fluid. If it wasn't, if the fluid was denser than the crystal, you'd never get a crystal. You'd never get crystallization. One question is it always true that the densest phase is crystalline? And we're going to look at that a little bit. That's a question we can ask. So after lots of work like this, people came up with a phase diagram from simulations as well as from some experiments, that what the phase diagram should look like for hard spheres is you should have a liquid up to 49%. You should have coexistence of liquid and solid up to 54%. You then would expect to have a crystal phase all the way up to 74%. But in experiments that were done and in early computer simulations, there was a glass phase which came in at about 58 to 63%. Okay. A beautiful experiment was done by Peter Pusey and Van Meegen in the 80s. They took colloidal particles
and they change their volume fraction. Here they're just sitting in the lab for a long time to sediment and come to equilibrium. And here you see a cloudy phase, that's the liquid phase, cloudy, but you start to see crystallites forming on the bottom there. That's the denser phase compared to the disordered phase over here. Then you see crystal, crystal, crystal. Then you see a crystal phase over this disordered phase, which just looks milky. And in these two samples, they said, oh, that's the glass, okay? So this is a beautiful experiment, okay? The only thing wrong with it shows, that you get crystallization as expected in a very clean system. The only thing wrong with this experiment is costs about $10, okay, to do. So if you're in a physics department, how are you going to impress your particle friends with a $10 experiment? So the question is, how can you make this, more expensive? Answer. You send it into space. $500 million just to lift off, right? Now, of course, it's really not that big because there are 500 experiments in this launch. But that's what we did. We sent it up to space to see what we could see about this glass phase, which we didn't quite understand. And so here is our plot. This is in 1998, okay? And here you can see a liquid phase. You can see the coexistence over here, just like they found over here. We found some interesting things. We found that the growth mechanism was dendritic growth, like snowflakes. That was kind of interesting. But we didn't find any example at all of a glass phase. The glass phase is essentially due to gravity, due to sedimentation, due to the fact of being out of equilibrium, okay? When you do that, okay. The glass phase then disappeared from simulations as well. That isn't because we showed that the glass phase doesn't exist. That's because the previous simulations were done with older computers so they could only use smaller samples for a shorter amount of time. Once they did this, once they got more modern computers with more memory and stuff like that and faster, this phase disappeared on its own, and now everybody agrees that theoretically this isn't there. You just are going to get a crystal for the rest of it. Okay. Now there's one problem that's still left. I told you that FCC is the densest packing. And it's true that it is. But on the other hand, there's a big degeneracy, right? It's not the only structure that has that density. If the FCC structure looks like this, it's face-centered cubic. Here's the cube. Here's the guy sitting in the face, etc. If you look at a different cut of the crystal, you see this hexagonal lattice over here. And in fact, the hexagonal lattice is the densest packing in 2 dimensions. And it turns out the way you might expect to get the highest density is simply to pack these layers on top of one another. The problem is, however, there are several ways of doing it. One way is you take one layer and you place it on the interstices on the layer underneath, but there are 2 ways of doing that because there's an interstices, there's a dimple there and a dimple there, and you can start the hexagonal crystal there or there. This would be A, this would be B, this would be C, and if you do ABC, 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 that's a face-centered cubic lattice. If you do another stacking, AB, 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 that's hexagonal close packed. In fact, you can make any arrangement you want of these layers as long as you don't repeat a layer and it has the same packing fraction, 74%. Okay? So this is still sort of an open question. It was looked at by Don Frankel and David Hughes and their students, partly because of some of the experiments we did, but in any event, they did it. And what they found is that FCC actually wins by 2 times 10 to the minus 3 in energy when they calculate the energy, which is essentially the free energy, which is calculating essentially the entropy.
So we wanted to see whether we could see this. So we did another experiment in space, okay? And here's what we got. This is the upper layer of a sample that's essentially in a capillary tube, a flat capillary tube. You can see the triangular lattice there. You can see that we're looking at it with a confocal microscope. This is the upper surface. You can see we've got these stitched together. We've got them stitched together in what's considered a monster crystal, because usually the crystals that you get from colloids are maybe a millimeter or a tenth of a millimeter, something like that. And this one was 2.7 centimeters by 2 millimeters by less. And this is the upper surface, and it is a crystal. Whether it's exactly a single crystal is something that we're still looking at, but you can see it looks great, okay? But better than that, with confocal microscopy, you can go in and you can take slices, slice, 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 slice. You can stack them together in a computer and see what you got. Well, one of the things you get when you look at it is just the top surface, which looks like what you see in Bernal's picture over there, which is this hexagonal lattice or triangular lattice over here. But then with the computer, you can just take the image stacks and you can rotate it. And when you rotate it to 54 degrees, 54.7, what you see is this, which is a square lattice. And the characteristic of having three-fold axis and a four-fold axis, in fact, 3 four-fold axes and 4 three-fold axes, is an undeniable definition almost of an FCC lattice. So this experiment essentially proved that, in fact, FCC, and not any of the other ones that you can make, not any of the other stackings, is really the ground state. I better speed up. Okay, now I want to get back to the random packing. So FCC wins even thermodynamically. Chaos, not just the densest. So this random close packing problem evolved while we were out of the game by people that were looking at what's now called jamming. And jamming is where you have a system, and by the forces between it and the density, you end up with something that's rigid, that you can't shear, okay? And it turns out the candidate for the endpoint over here, which is called point J, jamming point, is RCP. And that's sort of the question, whether that works. Okay, so it turns out that random close packing, the reason that it's a hard problem is it's got a restriction to it. It's random, but it's close packed, which means you have particles that are impenetrable. So one of my former colleagues at Princeton, Sal Torquato and Pablo de Benedetti, wrote this question, is random close packing well defined? And I argued with Sal for decades on this question. Every time we saw each other, we argued about it, because I would say, was obvious that there's no definition for it. And at one faculty party one time, I ran across John Conway. John Conway is one of the best mathematicians of the 20th century, came up with the game of life, and also was an expert on packing problems. I said, how come you guys haven't tackled mathematically random close packing? And he said, well, you know, random, you know what that means? Random, like a random numbers, means they're uncorrelated. You pick up numbers randomly from some pot that you've got, okay? And the idea is there's no correlation between the numbers you've picked up and the next one you pick up. And he said, the problem is, if I'm dealing with hard particles, there are correlations. I don't let them interpenetrate. So I've already got a correlated system, okay? So what do you mean by random? I've already gotten rid of some of the randomness. How uncorrelated, or what other correlations do I have to break to not make it, you know, to make it random? How long, what can I call random now if there are correlations? So he said it's an impossible problem. It's just not well defined, okay? Which is essentially true. So still today, we lack a definition of what random close packing is. Excluded volume gives you correlations. Okay. So then in this arguments we were having about, random close packing stuff, we asked the question, which I think is an interesting one and has not been solved yet in any way that I know, which is whether any shape packs denser randomly than it packs as a crystal, right? So everybody in this room has an intuition, okay, that in order to get the densest packing, it should be crystalline. It should be ordered. It shouldn't be disordered. And there's no reason for this. It's just something that you have as an intuition, except, as one of my colleagues, Dave Pine, says, except for the fact that your mother told you that if you fold your clothes up, when you put it in the drawer, it'll pack better. But aside from that, there's no proof, only a mother proof, okay? And so we wanted to look at this problem. Does anything pack denser randomly than as a crystal? I should mention that, in fact, the answer is nothing that anybody has found yet packs better randomly than in a crystal, okay? Oops, I didn't want to do that. Push the wrong button. Okay, but we said, let's try some things. And the first thing we said is if you're going to deviate from a sphere, the next thing you should try is probably an ellipsoid, where you're going to get lots and lots and lots and lots of exactly the same shape ellipsoids cheaply. And the answer is, okay, M&Ms. M&Ms are ellipsoidal, okay, ellipsoids of revolution, as a matter of fact, to better than 0.5%. For instance, if you chose Skittles, Skittles are off by 3%, okay? They're not what you want to use for this experiment. So we did the experiment, and we found, first of all, that M&Ms pack better than, randomly, they pack better than spheres do. Here's what spheres are at 64, essentially. Here's what M&Ms are when you use the biggest container with the smallest M&Ms, okay? It's like 69%, okay? Which is there. And then for a while, we tried ellipsoids that had three. These have, M&Ms have, or ellipsoids of revolution. So there's another axis we could play with. And we played around with that, and we got something that actually packs better. This is random packing of M&Ms. Well, actually, this is not of M&Ms. This is when we started doing simulations and computing what's the best we could get. And we actually got an ellipsoid which packs better randomly than spheres pack crystalline. And for about 6 months, we thought we had found something that packs better randomly than crystalline, okay? But then we thought about it for a while, and we discovered another way of packing, which beats it by that amount. The crystal of these 1, 2, square root of 3 packings was 0.75 and 0.75 and 0.76, essentially. So still nothing packs better randomly than it does crystalline. Okay, so what can we say about the random packing again? And I should speed up. Well, one of the things is, this is something that came from Maxwell. Actually, it's kind of nice because you learn this in public school. So Maxwell said, if I want to have a stable configuration of particles or of bridges or of anything that I want to make, okay, then the one thing I have to be able to do is determine the position, okay, of all of, let's say, if I have a mound of spheres, the position of each and every sphere. That means the unknowns that I have to satisfy, okay, have to be x, y, and z for each particle, so 3 times the number of particles, okay? That's the number of solutions I'll have to find by something. And the only way I can have that many variables and solve them is if I have that many equations. So what do I get equations from? The only thing, if I tell you I just have a mound of spheres, the only thing that give me equations are the equations for where their contacts are, right? And to make a contact, okay, I need two particles. So the number of equations, okay, is going to be, the number of variables is the dimension you're in times the number of particles you're in. That has to equal the number of equations you have. That has to give you, that's the number of contacts. Each contact involves two neighbors. So what it says is the average number of neighbors you have to have is twice the dimension you're in. So for random close packing, which is in 3 dimensions as we used this so far, what you need to have is you need to have 6 contacts per particle, on average. It doesn't have to be each particle with that, but on average, that's what you need. If you take M&Ms, okay, they are ellipsoids of revolution, so that means that what I need is I need X, Y, and Z, and I need an axis with 2 angles, okay? So that's 5 degrees of freedom. That means I need 10, okay, on average. And when I had a summer student count the number of contacts between the M&Ms here, right? Here's what he got, and this computer simulation gave the same. It's centered on 10 like that. And all of you thinking, oh, this bastard had a poor student, okay, spend the summer counting the number of contacts. First of all, the way you count the number of contacts is you pour paint in, okay, you drain the paint out. If the particles are close together, they leave a little meniscus. If the particles are actually touching, there's a clear spot in the middle of the meniscus, okay? So you spend your summer doing this. He sort of partly figured that out. That's a cool way of doing it, okay? And that student got a science paper out of it. He got a full fellowship to University of Illinois, Champaign-Urbana, okay? He got a postdoc at École Normale in Paris. He got an assistant professorship at MIT, and in 1 year after that, he got a full professorship at MIT, a full professorship at Caltech, and he's the director of Max Planck. Okay, so he did good. You shouldn't feel sorry for him, right? Okay. What?
How many MMs did he eat?
How many MMs did he eat? Oh, maybe that's how he got this number. Okay. Anyway, okay. So having this number, having Z is equal to just the minimum number that you need to solve the problem, okay, is called being isostatic, okay? And here's an example of something that's isostatic. If you have a stool, you have to prevent it from going up and down, right, left and right, and forward and backward. So you have 3 degrees of freedom you have to compensate for, and there's just enough here, okay, 3 legs like that. This is more than enough, that's not enough, right? So isostatic means that you have a configuration like that, the minimum. Okay, now I want to get to the point that I wanted to get to. Let's see how fast I can get through this. Okay, this is a demonstration by G.I. Taylor, who is an absolute genius in lots of things. He discovered dislocations, topological defects. He also did lots of work on aerodynamics. He learned how to fly a plane in World War I in order to figure out the aerodynamics of it. And he did great things in looking at instabilities, at hydrodynamic instabilities. Here is a demonstration he did of the fact that low Reynolds number flow. So if you have a very viscous fluid, the flow is reversible. It essentially means in this case that your fluid is slave, okay, to the motion of the boundary. So if I took two concentric cylinders like that, I put the fluid between there. The flow inside is completely determined by how I move the boundary over here. These are Stokes equations. That's appropriate for low Reynolds number flow. Watch this movie. If you have seen this movie before, okay? If you haven't seen it before, it's the only thing you're going to remember from this talk. Okay, here's what he does. Two concentric cylinders, viscous liquid between them. He puts some ink down there, okay? He goes around like this with his finger, okay? And he's shearing the fluid, right? And it looks like the drop of ink is disappearing, okay? Now, if he runs the movie backward, we know what's going to happen. But he makes sure he's not running it backward, puts his finger on the other side. He's not even being very careful about going at the same speed, okay? But he's just unwinding this thing. And when he unwinds it, comes back. Isn't that amazing? Anyway, that's really great. Okay, so one of my colleagues, Dave Pine, okay, said, oh, maybe we can screw this up by adding some particles inside. What happens if we put particles? Is it going to be that if I move it back and forth like that, and it depends on how, and shouldn't depend on how much I move it, but in any event, if I move it back and forth, are the particles going to come back to their starting position? And he matched the density in here, and the index matched it so you could see what was going on, stuff like that. And the answer was weird. What he found is, indeed, these are strobed images, okay? So what you do is, each time you move the cylinder, rotate it one way, and then you rotate it back, you take a picture. You rotate it forward, you rotate it back, you take another picture, okay? And here, as you see, the particles which are going back and forth like that, if you strobe it, you can see that these particles, by the way, you can see it's a movie because something is falling in the background over there. So this is actually a movie, okay? Strobed, okay? And these guys are coming back essentially every time. But above a certain threshold of the strain, that's essentially how much I'm rotating it, okay? They're chaotic again. They're all moving around. They're diffusing. These guys aren't diffusing. These guys are doing some weird diffusion, okay? And there's a real threshold here. Below that threshold, essentially you see the particles don't move, and then after that threshold they move anisotropically in the direction or perpendicular to the direction of shear. And the explanation they had was they said, oh, well, it's known to some people that that 3 particles can be turbulent and 2 particles you can solve for exactly. You can solve for the motion of a particle, you can solve exactly, you can solve, this is classically, you can solve the motion of 2 particles exactly by going to center of mass. If you get to 3 particles, it's, you can have, what do I want to say? They can, what's the word I'm looking for? No. Anyway, 3 particles, you know, can be chaotic, okay? Which means they're exponentially sensitive to their initial position, okay? And I didn't like this explanation because the claim they were making is that the particles were random, okay? And if you have random particles, sometimes you have 2 particles close together, sometimes you have 3 particles close together, sometimes you have 4 particles close together, right? So there's nothing really special about 3 particles in that case. The idea being that the more I get more contacts or more interaction with particles if I shear it further, okay? So those guys, the guys who did this were Dave Pine and Jerry Golub, who were pretty smart guys. So I said, well, I have to do something to show them if I'm going to disprove them, right? If I'm going to disprove what they're saying, I have to do something to show them. So I said, well, I'll do a simulation. I'll put in just in the simulation that I throw particles down. I'm going to shear them. If when I shear them, they interpenetrate. This is a simulation, so these are phantom particles. They touch one another. Then when I bring them back, they're going to have moved from that position, okay? And I don't know how to do that. That's complicated. That's hydrodynamics, and it's friction with the sample and everything. It's really hard. So I said, can't do that. So I'll do the easiest I can. If they touch, I'll just say I'll bring them back to their initial position, which looks like that, and I'll give each of them a little shove, right? A little push in one direction, a displacement, okay? And this is like the movies that I showed you in the first one, although here I'm shearing it. So I'm strobing it again so you don't see the backward and forward motion. This is above the threshold field. This is below the threshold strain. It looks as if some of these are dead or not moving, but you'll see they get infected, okay, by others. And now as time passes, you see what happens is these guys over here, the number of active ones, which are the ones in red, okay, are getting fewer. And over here, they're essentially staying the same until finally all of these are absorbing. All of them have found a position where they don't touch anything, even though I've sheared it a certain distance. But if I sheared it further than that, okay, now I never find an absorbing state. And you say, oh, what if you wait longer? Well, you wait longer. And if you're above the threshold, what you find is it goes to a steady state, an active steady state over here. This is the activity, the number of particles that are touching one another. And below, it dies to zero. It's kind of interesting, okay? Moreover, what you find is you can characterize a time at which this one goes to zero or a certain fraction to zero. And this one you can characterize a time, okay, at which you go to steady state. And if you look at that time as a function of how much you're shearing it, which is over here, you find that it diverges on either side of this threshold field. And that's a signature of a second-order phase transition, okay? It's not a thermodynamic phase transition again, it's a dynamic phase transition, or dynamical phase transition, but it's a phase transition. And that's kind of interesting. Okay. And here's what it looks like for longer times. There's actually, if you're lower than the threshold, you die to zero. There's a separatrix, which is where you're at the critical state. And above that, you keep on active forever. Now I'm really going to speed up. Turns out while we were doing some of this work and arguing with Sal about the M&Ms, Sal Turcato was co-author on those papers. I was also working with Paul Steinhardt on seeing whether quasicrystals, like this icosahedral quasicrystal over here, would make good photonic materials. I don't know. Why did we think that? Because it's more isotropic. An icosahedron is more isotropic, going to be more uniform in direction than any conventional regular crystal. Okay? And we were working with this, and we were looking at regular crystals. So this is a diamond lattice over here. These are the Brillouin zones. We found here that actually quasicrystals have Brillouin zones, which is kind of cool. But Sal was asked me one day, well, let's not talk about M&Ms today. What's this that you're doing with Steinhardt? So I said, we're trying to look at quasicrystals for photonics. And he said, oh, I can give you something that will give you a gap for photons. It will be a photonic material, and it's completely isotropic. Here, it's not completely isotropic. It's got 5-fold symmetries and 10-fold symmetries and things like that. He said, I'll make you something that is neither a crystal nor a quasicrystal, but has a photonic band gap. He says, I know how to do it. We just discovered this thing. So here's Sal and here's me while we're working on the M&Ms. What Sal said is, let's look at the following problem. Suppose we throw particles down randomly, let's say here in 2 dimensions, but we can do in 3 dimensions, okay? And we ask how many particles there are in a circle that I draw there. Well, the answer is it's just the area of the circle times the density. That's fine. Okay. Then he says, now suppose we move this around. Okay. If we move this circle around, so I may take it from there and I move there, I'm going to get a different number. It's going to be approximately the same, but it's going to be a different number. And you can ask what the variance is, and you know already because you've done some statistics and you've done things with random walks and things like that. You know that the variance there is just going to be equal to the average number of the particles. Delta n squared goes like n. And n, if I've got a well-defined density for the system, goes like v, which goes like r to the d. So in d dimensions, I can just generalize this. So for a Poisson or random distribution over here, what I'm going to get for my variance is just r to the d. And then the question is, can I do better than that? And everybody raises their hand, yeah, of course you can do better than that. You can do a crystal, okay? And sure enough, when you take a crystal and you move this around, the variance is less than it is over here. But your intuition is, it's not going to vary at all, and that's not true. The reason it's going to vary as I move it around is sometimes that point is inside the circle and sometimes it's out of the circle. So what I'm actually going to get here is a variance that doesn't depend on the volume, but depends upon the perimeter here, or the surface if this were a sphere. It goes like d minus 1 instead of like d, okay? And what Sal said is, well, in fact, I can make something in between this one that's really random over here, where I get r to the d, and when I get r to the d minus 1, you can't do better than r to the d minus 1 unless you have no points. You just have a continuous background. That, of course, you move your circle around and the mass won't change inside. But anything else will. By the way, one of the things that this tells you is the fluctuations typically are measured by doing a scattering experiment or measuring S of Q, the structure factor, S of Q. And the characteristic as wavelength goes to infinity is to have Q go to 0, wave number go to 0, and the characteristic of something which is less than D in terms of the fluctuations is that S of Q goes to 0. And in fact, if the variance goes like r to the d minus alpha, then S of Q goes like Q to the alpha. I don't have time to really go more into that than that. Here's a hyperuniform structure. A little bit funny, okay? It's clearly not periodic, and it's clearly not random, right? It's pretty obvious, okay? And here's one that you would make if you made something that would hold together. It's just decorating sort of a Voronoi construction that you could make on these points. And sure enough, when you make it, this is a square lattice, that's a hex lattice, that's a quasi-crystal. All of these show Bragg scattering. Here's a hyperuniform disordered material, okay? And it has an even bigger photonic band gap. This is where light doesn't go through. And it doesn't have any Bragg scattering. It has an S of Q that looks like that, and S of Q is dying as you go toward the middle. Kind of interesting. Okay. Now, what does this have to do with anything I told you before? Okay, the answer is, one of my buddies and co-conspirators on lots of things is Dov Levine, who's at the Technion, and he and his students showed that at this critical state of this process, which we now call random organization, okay, of this dynamical phase transition, the system at the critical state is hyperuniform, and the hyperuniformity goes like an alpha that's 0.45 in 2 dimensions and 0.25 in 3 dimensions. This is wild. It's wild because it says for this kind of a transition, okay, when you get to the critical point of the transition, your fluctuations are suppressed. Exactly the opposite of what happens in a thermodynamic phase transition, right, where the fluctuations grow. As a matter of fact, the correlation length goes to infinity. and you end up with a fractal-like structure. So this is what, for instance, critical icing looks like. And this is called critical opalescence. So you get exactly the opposite now for this model, this random organization model, this dynamic model. So we wanted to see whether it was true. So Sam Wilkin did his thesis on it. He took a confocal microscope. He did something that's sort of like a Conan plate rheometer over here. You do this so that when you move this around, you get the same strain over here as you have over there. Okay, and here is the sample. It's dyed fluorescent, so you can do confocal microscopy on it. This is essentially to prevent things from evaporating. Okay, and he came up with a clever way of finding out when you get to the critical point. What he does is he takes the sample, he goes to a high shear amplitude, okay? So you're up here, and you go to this steady state over, you're going toward this steady state over here of an active system. You then go 400 cycles there. You stop, you take a picture, you reduce the strain to there, you let it go 400 times, you take another picture, you let it go 400 times, take another picture. The first time you cross the separatrix over here, your path changes from active to absorbing, and this thing goes down to 0 and stops. Now, I just love this. So here I'm going to show you a slice of the sample. It's a three-dimensional sample, but we're taking a confocal slice of it. And here the liquid is dyed, so that's what we're seeing. So the black dots are the colloidal particles. And over here, I'm going to show what the strain is. And so what you'll see is when the strain is going full, this thing will just be going crazy. And then as it approaches the critical strain, it will slow down. As it goes through it, it will stop. Watch this. Boom. See that? And over here, where it absolutely stopped, I've changed by maybe 10% the amplitude of that shear. Okay? Is it hyperuniform? So we take the samples, we look, this is what S of Q looks like. It's got squiggles over here, which tell you about the correlations of close neighbors. Okay? And over here, this doesn't look great, but you can see that at critical, it's about the right slope. Here, we go past critical, which is the wrong slope, and this guy over here is at critical. And here's another one at critical, and separate, they don't look great. You put them all together, you can see you've got more than an order of magnitude of slope there, where you can say that indeed it's hyperuniform with a exponent that's 0.25. Okay? Okay. Now, it turns out when Sam did the experiment, what happens as you change the displacement that you give an overlapping particle, the kick that you do when two particles are touching one another to separate them, determines it's one of the things that determines what the critical state is, what the critical value is. And for the model that we're using, straight random organization as we call it, it's limited. And the reason it's limited is because it isn't what you actually find in the experiments, the critical value, because you're dealing with phantom particles. So they're missing some of the correlations that the hard particles would do. So he said, let's see whether we can do better than this. He was a clever guy. He is a clever guy, okay? And so he says, okay, let's do the following. Instead of giving, if they overlap them, a random kick, this one that way and this one that way, sometimes they're going together, sometimes they're going opposites, sometimes they're going different. What we'll do is put in a little bit that's repulsive, okay, and see what that does, okay? So you put in a little bit that's repulsive, one displacement out of 10 to the minus 3 is repulsive. You find then that instead of having this guy, which is going to 20%, it gets higher and higher, and it's pointing somewhere over there. And then you do it, let's say, where all the kicks are repulsive, and then it's this curve. And look where it's going. It's going to 0.64. 0.64 is random close packing. What the hell, where did that come from? Okay? So we don't know. But in fact, a linear extrapolation, even that, this is log, so you can't extrapolate as well. A linear extrapolation says it hits right there. So you say, well, is it really random close packing? Let's see what other people call random close packing. So it turns out the correlation function looks the same. You have no, well, of course, the particles don't overlap one another. That's why this is 0 over here. But you get a spike, and then you get a tail. You get this characteristic double peak over there. The way you approach infinity here, okay, is a divergence that's the same that other people looking at what they call random close packing find. The isostaticity, which the people that were trying to find random close packing put in a requirement that you had to have isostaticity, that Z, the number nearest neighbors, had to be 6. Here, it's emergent. We didn't put anything like that in. All we said is, what's the densest we get with this model? What's the critical point that we get, okay, between the densest critical point we get between the absorbing and the active phase? And when you look at it, it's isostatic, okay? Then we say, well, is it in the same active universality class, okay, as what we started with? If we add this extra thing where instead of having a random kick, you have a directed kick, and you find that all the exponents that are associated with that phase transition, I only showed you one of them, the critical slowing down, but they're exponents for lots of things, and they're all the same here. And then you look whether what you get here for the densest state is hyperuniform, and it's hyperuniform like that. And then you go back to the literature, which has published results for random close packing. And here are, for example, 2 of the published 5 years ago or something, results for random close packing for the structure factor S of Q. And the red guy here is what we find from this, what we call biased random organization here. And they're indistinguishable. And you might say, oh, well, maybe we're using a hidden way of doing the same process everybody else used. But if you go away from this critical point, you find that the 3 different methods give you different SFQs. So it's not just the same thing. Okay, so I better end. I should just say now that one of the things we might do is ask whether this new way, this dynamical transition, may serve as a definition for random close packing. If you do that, you get the right numbers, or you get numbers that agree with what other people have found in 3, 4, and 5 dimensions. In 1 and 2 dimensions, you find out that it actually crystallizes, which is what other people sometimes find. And you find all sorts of other things about it. You find that, in fact, it's the same universality class. One of the interesting things is people have looked at, they've looked at the hyperuniformity. Let's see, am I looking at the right one? That's Z, what we found in 2, 3, 4, and 5 dimensions, all give you, they're isostatic. In 2 dimensions, the number of neighbors is 4. In 5 dimensions, the number is 10. This is not like the M&Ms where you've got your other degrees of freedom come from rotations. And then the thing that was kind of cool in particular is, let me see where I have this, is that Giorgio Parisi, and some of his collaborators did a calculation of what's called the gap function, which is when you have random close packing, some of the particles are touching, some of the particles are near to be touching, and these guys did what turned out to be a real tour de force calculation with replica symmetry and stuff like that to find out what the distribution of neighbors were, okay? And they could only do it in mean field. And mean field means above the upper critical dimension, that should work. If you know that, you know it. If you don't, believe me, okay? And when we looked at it, this is plotted in such a way, is that the one that's plotted the right way? Okay. That when this is flat, okay, you get the mean field result. The mean field result, I didn't write it here, is 0.42. And in 2 dimensions, we get 0.58. In 3 dimensions, we get 0.5. In 4 dimensions, we get 0.42. In 4 dimensions, we get 0.42. In 5, we get 0.42. So it looks like these are the upper critical dimensions, right? And that's an interesting fit, which is not found by other people who are working on the problem. And I will leave it simply with this. If we are lucky, it looks like what this model does, bias random organization, is it gives us what random close packing is like in different dimensions. But now the thing that I haven't told you, because it's another colloquium, okay, I've already gone over, is if you take the system and you shear it, okay, then it turns out instead of, if you shear the system and you break symmetry, then you get FCC in 3 dimensions, okay? And you get the crystal structure, which people think is the crystal structure, in 4 dimensions for the densest packing. So it could be that we have, by this, for a reason that we don't yet understand, by these simulations, a way to get maybe the densest random packing and maybe the densest crystal packing. And that's interesting because the only thing that was known exactly till 2 years ago was the densest packing in 1, 2, and 3 dimensions. And now, within the past 2 years, I can't pronounce her name. I think, anyway, she won a big prize for this. She found the densest packing in 8 dimensions and in 24 dimensions, which is the Leech lattice. And none of these other dimensions is the densest packing known. And you say, well, who cares? We don't live in a dimension bigger than 4. But our computers do. And for instance, when you store a number with a number with a certain number of digits in it, that's the dimension of space you're in. And what people are interested in, okay, is finding the best way of packing information so that it doesn't overlap, so this bit of information doesn't contaminate this bit of information.